Hey everyone. So, I'm just really excited that we've gotten to day 3 of U subs and you're still here. It's so cool. So, let's see how many of these we can do. And maybe we'll have a quiz at the end. All right. Uh, Cosines. Oh, by the way, I don't think I'm dropping any bombs on you today, like in the last two videos. Okay, so these should all be doable with things we talked about in U subs 1 or U subs 2. Okay, we've got that. Sine theta, d theta. Pause the video, give it a try. So remember, this is the one that I said cosine theta squared sine theta d theta, where u equals that inside the squaring function cosine theta. And du would be negative sine theta d theta, or negative du is sine theta d theta. Well, I have a sine theta d theta, and that can be replaced with negative du, and here this cosine theta is u. So this integral becomes u squared times negative du. To avoid confusion, I'm pulling that negative out in front. And so now what can I do? What's the antiderivative of u squared? The antiderivative of u squared is u to the third over 3. Don't forget the plus c. And we don't want this in terms of u, we want it in terms of theta. So my final answer is going to be cosine theta to the third, and you could certainly write that as cosine to the third theta over 3 plus c. Okie doke. There's the first one. I can't wait to see what's next. How about this one? Integral cosine squared theta d theta. No, I'm not thinking u sub quite yet. No, this is power reducing. I need 1 plus cosine 2 theta over 2 d theta. I'm going to pull that 1/2 out in front. 1 plus cosine 2 theta d theta. And I'm going to split this into two integrals. Now, by the way, what happens is, if I don't split this into two integrals, you're going to do a u sub there, and it's inadvertently going to affect this. And we don't want our u sub over here to affect this, and the only way to really force that to happen is for us to split this into two separate integrals. It's not capricious whimsy that causes me to do this. It's the fact that I don't want to make a mistake. Okay, my antiderivative of 1 du is going to be d theta is just going to be theta. Here, I'm going to do a u sub where u equals 2 theta. So du equals 2 d theta, or du over 2 equals d theta. So that becomes u, and that becomes du over 2. So plus 1/2 integral cosine u du over 2. Let's pull this 2 out. And so now I'm looking at 1/2 theta plus 1/4 integral cosine u du. And we know that our u in this problem was 2 theta, so I've got 1/2 theta plus 1/4 sine u, and that's 1/2 theta plus 1/4 sine 2 theta. Don't forget the plus c. All right, that's our final. You got there? How about this one? The integral of secant squared theta d theta. Pause the video, give that one a try. Hey, welcome back. Hopefully you didn't suffer and instead you said tangent theta plus c. The derivative of tangent is secant squared. Yeah. So remember when I said, no, you really need to know all your derivatives from chapters 3 and 4. No, you really do need to know them all. You need to be able to recognize that is that. Okay? Now, if I had something like this, what I would say is, okay, 1 over secant squared, that's cosine squared, and then I used my power reducing identity. And what if I saw this? What can I do with tangent squared x dx? I don't want to split this up into sine squared over cosine squared. I could, but I really don't want to. And instead, I want to think about a Pythagorean identity I know. Remember that secant squared x equals 1 plus tangent squared x. So tangent squared x is going to be secant squared x minus 1, because I subtract 1 from both sides. So this thing that I was stuck with, I can rewrite as secant squared x minus 1 dx, using that Pythagorean identity. Again, we learned the Pythagorean identities for a reason. This was the reason. Okay, so what's... Oh, I wanted to split this up into 2 integrals. The antiderivative of secant squared is tangent, minus the antiderivative of 1 dx is x plus c. All right, look at that. Tangent squared's integral is tangent x minus x plus c. Wow. Gotta know my Pythagorean identities. Okay. How about, speaking of things that look the same but are different, how about this one? Sine squared x dx. Pause the video, give that one a try. Come back when you're done and you want to check. Okay, welcome back. Well, that's power reducing. 1 minus cosine 2x over 2. And I split this up into 2 integrals. I don't want to take the 2 out first. Half 1 dx minus 1 half negative cosine 2x dx. Okay, so a u sub, u equals 2x, du is 2 dx, or dx is du over 2. So that can be replaced with this stuff, that can be replaced with this, and I think I'm going to pull that negative out. Negative times negative makes a positive. In fact, I could do this integral over here, plus 1 half cosine u du over 2. Again, let's pull that constant out. 1 half x plus 1/4 integral cosine u du. Antiderivative of cosine, yeah, that's got to be sine. 1 half x plus 1/4 sine of u. Remember, u was 2x. Don't forget the plus c. There's our antiderivative of sine squared. Have to use power reducing identities for that, please. There is a path that uses a technique called by parts, and many students find that much harder than doing this. Okay? Hey, what would you do if you saw this one? 1 over sine squared x dx. I'll give you a hint. It's not power reducing. That's right. I can turn this into the integral of cosecant squared x dx. Hey, I recognize you. You're the derivative of negative cotangent x. Right. Kind of looks like power reducing, but really, it's something I recognize. And yes, I do need to be comfortable with reciprocal identities. This is why we did trig and made sure we were comfortable with all those identities. Okay? Hey, what if I see this one? Cosine, oops, sorry, that's all under a radical, 3x times sine 3x dx. I guess we could write it this way, sine 3x dx. Okay, so I guess, I want to start with u equals cosine 3x. All the stuff here not only inside another function, but also in a denominator. I mean, it's screaming for me to make it the u. Du, well, the derivative of this is going to be negative sine, leave the inside alone, times the derivative of that inside function, negative 3. Hey, don't lose the dx. So I see sine 3x dx here, and there's a sine 3x and a dx there. So I think du divided by negative 3 will be sine 3x dx. And so I can replace all of this stuff up top just with that. And on the bottom, well, that's u. So this could be 1 over square root of u du over negative 3. I'm going to pull that negative 3 out. It's on the bottom. It needs to stay on the bottom. And here, instead of writing with the radical, I'm going to go with negative 1/2. For me, I'm much more comfortable finding the antiderivative of this than the antiderivative of that. So I've got 1/3 antiderivative here, 2u to the positive 1/2. How did I know? Well, I add 1 to this, that gave me that. And I thought, okay, if I take the derivative, a 1/2 has to come down in front. And I don't have a 1/2 here down in front. So there must have been something present on the original function so that when I take the derivative and that 1/2 comes down, it cancels because I don't have anything here. It's all gone away. Okay. Yes, by the way, your book would like you to think about it this way, where whatever this power is the same. I'm just doing a flip and multiply here to turn that into 2. Okay? So we did our antiderivative. We've got 2/3 square root of u plus c. And remember our u was cosine x. 2/3 square root cosine 3x. Don't forget the plus c. All right, here's that one. How about this one? Integral cosine x over 1 plus sine squared x dx. So what are you thinking to do here? What looks promising? Does it look promising to split this into 2 fractions? Yeah, no, it doesn't. Not to me. Should I use a power-reducing identity here? Oh, definitely not. Do I have a Pythagorean theorem, a Pythagorean identity that fits here? Yeah, so no. No, I remember that sine squared plus cosine squared equals 1. And if I subtract sine squared from both sides, I don't get 1 plus sine squared, I get 1 minus sine squared. So it's a good thought, but not for us. What if I make my u 1 plus sine squared? So my du is going to be 2 sine x dx. Oh, wait, I forgot the derivative of the inside sine function. Cosine x dx. Okay, so what can happen here? Well, I can make this part, I have, so yeah, I've got a little problem there, don't I? Well, let's see what happens. We're going to have 1 over u, nice, but we've also got this du over 2 sine x is equal to cosine x dx. So, yeah, guess what? That's still in terms of x's. That's not a happy place, is it? No. Sad face. Hey, what if we were a little smarter? Okay? What if instead of taking this whole denominator, we said that u was just sine x? So then du would be cosine x dx. Oh, well, I have that. So this becomes the integral of 1 over 1 plus u squared times du. Oh, look. look at you, your inverse tangent. Wow, I didn't see that when I took the whole denominator. So here we've got inverse tangent of u plus c, and let's plug our u back in. So we've got tangent inverse of sine x plus c. Hubba hubba, as my grandmother used to say. Yeah. Okay, how about this one? The integral of ln of x over x dx. You should be able to do this one. Hey, welcome back. I see a u sub here. I see a function. And what's the derivative of ln of x? 1 over x. So u is ln of x. du is 1 over x dx. There's 1 over x dx. There's ln of x. And so I'm writing this as u du. I mean, I'm sort of speechless. Like, this is sort of chunky stuff. And if I showed this to a pre-cal student, they'd probably run away and not take calculus. But now when I get to this, what a nice, gentle antiderivative we're making here. And don't forget to replace u with that stuff in terms of x. So we can write that as ln squared over 2 plus c, or you could write it as ln of x squared over 2 plus c. All right? Okay. How about this one? Integral of cosine square root of x over square root of x dx. Okay, give it a try, do some thinking. You know, it may well be the case that the first time you watch this video, you're just sort of being overwhelmed and exhausted and writing everything down. So maybe I should say, hey, if you didn't do this the first time around, maybe you should definitely do this if you watch the video again. Because what I see is that u is square root of x, or x to the 1 half. Why? Well, let's take the derivative. We've got 1 half x to the minus 1 half dx. And what's that? That's 1 over square root of x dx. And I've got 1 over square root of x dx. I want to get rid of that 2 by multiplying sides by 2. And so I can replace all of this stuff here with 2 du, and this with u. So my integral is going to become cosine of u times 2 du. I'll pull out that constant. Antiderivative of cosine? No problem. 2 sine u plus c. And what was our u? Square root of x. So 2 sine of square root of x plus c. There's our antiderivative. And remember, you could always check, and I kind of recommend that on the test you check. You could always test this by taking the derivative of this. Okay, so the derivative of sine would be cosine square root of x, but don't forget the derivative of the inside function, which is 1 half x to the minus 1 half. The 2's cancel. I've got cosine root x on top, and on the bottom, square root of x. No kidding. And of course, the derivative of a constant is 0. Nice. All right, how about this one? Integral of 1 over x squared. Let's go with 4 over x squared plus 25. Okay, there's my integral. Please tell me what the antiderivative would be. So yeah, I did pull out that 4. And then I said, ooh, this is inverse tan. If I divide by 25, and simultaneously in the denominator, multiply by 25. So we've now got 4 over 25, integral 1 over x squared over 25 plus 1 dx. This, well, if I take the square root of top and bottom, is my u. So I know that du is 1/5 dx, where dx is 5 du. And this, well, if I square both sides here, I get x squared over 25 equals u squared. So that's u squared, and that's 5 du. So 4 over 25 integral 1 over u squared plus 1 times 5 du. Well, that 5 can come out, and that 5 will then cancel with 25, leaving me 4/5. The antiderivative of this is tangent inverse of u. Don't forget the plus c, and don't forget to do that replacement. 4/5 tangent inverse x over 5 plus c. Really, they don't get any easier until you actually do them. Please do them. Don't just watch me doing them. You need to be this comfortable with them. Okay, so what do we do here? Is this inverse tangent? No, it's not inverse tangent. Not with that on top. This is a u sub. Look at my u. The derivative of this, 2y dy. Oh, I've got y dy. So u is going to be my denominator. So du is going to be 2y dy, or y dy equals du over 2. So this can then be rewritten, since I have y dy, as du over 2, and my whole denominator was my u. 1 over u times du over 2. Pull out that 1/2. And now I know I'm looking at ln's derivative. So 1/2 ln u plus c, or 1/2 ln, there was our u, y squared plus 25, plus c. Don't forget the plus c. Y absolute value here and not here. This is always positive, so we don't need. And yes, of course, you can just keep writing the absolute values. That's fine by me. Okay, so we've done a lot of these. Let's take a look at just this one then. And then I'd like to do a couple of, evaluating. I want to do some definite integrals. Because even though I know you're comfortable with that, yeah, not unless we practice. Okay, here you go. Please take care of that. Yep, it's a u sub where u is that inside function, square root of y, or y to the 1/2. If I take the derivative of both sides here, I'll get to u equals 1/2 y dy. Oops, y to the minus 1/2. Sorry. Well, that's the same as 1 over 2 times 1 over square root of y dy. Hey, I've got a 1 over square root of y dy. I'm just going to get rid of this 2 by multiplying both sides by 2. And then 1 over square root of y dy is this stuff. There's my u. So this is now going to be e to the u times 2 du. Pull that 2 out, e to the u du, and we know the antiderivative of e to the u is e to the u. Don't forget the plus c. And let's take our u and plug it back in. 2e to the square root of y plus c. Remember, you can always check your antiderivative by taking the derivative of your antiderivative. What would that derivative be? Well, let's take a look. We've got the derivative of e to the is e to the times the derivative of that stuff. The derivative of square root of y is 1/2, y to the minus 1/2, and that's going to be the same as these canceling. This is going to be the same as square root of y at the bottom and e to the square root of y on top. And that's exactly where I started. Derivative of a constant is 0, so I don't have to worry about that. You know, there are a lot of things to know here. And to make matters even more exciting, all these things, yeah, you can't forget them until after you take not only the AP exam, but our semester final exam. Actually, it's a year-long final exam. It's the final exam of the whole class. You can't forget this stuff. You really need to keep practicing it. And that's the reason why you have the integration and differentiation packet. You should be working on that. Okay? All right, so let's go now to definite integrals. So what do I do in this situation? The integral from 0 to square root of pi x sine of x squared dx. Okay, this is very different than if I were asking you sine squared x dx. I'm doing this one, not this one. Okay, so it's a U sub. Get along and do that U sub. Give it a try. Okay, so I hope you said that U was x squared. So the du would be 2x dx. Well, I have an x dx, so I'm going to divide here by 2. Du over 2 is x dx. And so I can replace this with u, and I can replace x dx with du over 2. So now we've got sine of u du over 2. I'll pull that 1/2 out. Well, that looks pretty friendly. Now, notice I don't have any boundaries here. If I take and put these boundaries on this problem, I lose points. Why do I lose points? And in fact, I'm going to get the wrong answer. But I'm losing points because these are the x bounds, not the u bounds. If I'm going to have a u, I have two choices: no boundaries or u boundaries. How do I find my u boundaries? Well, let's plug our x's in and see what we get. If I plug a 0 in here, 0 squared is 0. Good. If I plug a square root of pi in here, square root of pi squared is pi. These are my u bounds. So remember, your choices are no bounds or u bounds. Okay, I need u bounds here. So antiderivative of sine is negative cosine of u plus c. And I know that my u was x squared. So this turns into negative 1/2 cosine x squared plus c. But wait a moment, this wasn't an indefinite integral. This is a definite integral. And I can now evaluate this with my original x bounds, or I can actually stop here. Because of this u, I can use my u bounds. It is actually often faster, less complicated, less small mistake. No. To put your u bounds into your u antiderivative. But you should get the same answer whether you're using your u bounds with your u antiderivative or your original x bounds with your x antiderivative. So I've got negative 1/2 cosine of u. And when we do a definite integral, the c's are always going to cancel. So I'm just going to plug in a 0 here. And I'm going to subtract negative 1/2 cosine of pi. Okay, cosine of 0 is 1. And negative 1/2 times 1 is negative 1/2. Cosine of pi is negative 1. So I have negative 1 times a negative is another negative. And so I end up with negative 1. This is equal to negative 1. Who knew? Well, let's try evaluating here, but this time with our original x bounds. So what's going to happen here? Well, I'm going to plug in that square root of pi and square it. Square root of pi squared is pi. So I'm going to have negative 1/2 cosine pi minus negative 1/2 cosine 0. Okay, well, what does that get me? Cosine of pi is negative 1. Negative times negative is positive. It's very disturbing. I kind of want to go back and deal with that again. Because look, this is cosine of 0 is 1. Minus and minus is plus. Uh-oh, I got positive 1. So let's go back here to this one and make sure that I'm plugging them in the right order. So I'm plugging in the pi. Cosine of pi is negative 1. Negative times negative is positive. And now I'll plug in a 0. Cosine of 0 is 1. So I'm subtracting, that's the FTC part 2 minus this negative 1/2. Okay, because when we plug a 0 in here, cosine of 0 is 1. 1 over 2, that's this. And there's that negative out in front. And this negative is from FTC2. We got 1/2 plus 1/2 is 1. So even though I said as preamble, or pre-ramble, that this would be negative 1, and it's easier to plug in my u-bounds than my x-bounds, I, of course, then showed you that I'm a goofus. So, yeah, just be careful with FTC part 2. Here, how about this one? Practice with this one. 3x squared, square root, x squared minus 1. Oh, sorry, that's x to the third. X to the third minus 1 dx. And it's a definite integral from 1 to 2. From 1 to 2. Okay, give it a go. Hey, welcome back. Yeah, so I said u sub because I see a function and most of its derivative. In fact, all of its derivative. If u equals x to the third minus 1, du is going to be 3x squared dx. Ta-da! And so I can rewrite this as the integral of square root of u du. What are my u-bounds? My u-bounds, if I plug a 1 in here, 1 to the third is 1, minus 1 is 0. And if I plug a 2 in here, 2 to the third is 8, 8 minus 1 is 7. So this is 0 to 7 of u to the 1/2 du. Well, we know that antiderivative. We're going to add 1 there. U to the 3/2. But, if I take the derivative, there's no 3/2 there. So there must be something present, so that when I take the derivative, they cancel. And we want to evaluate this from 1 to 7. Well, if I plug a 0 in there, 0 is 0, 0, 0. So really, I only have to worry about 2/3 times 7 to the 3/2. And there's my answer. Using my u-bounds. Well, what if we didn't use our u-bounds? What if we rewrote this 2/3 x to the third minus 1 to the 3/2 and evaluate that with our original x-bounds from 1 to 2. So if I plug in a 2 here, 2 to the third is 8, 8 minus 1 is 7, and I've got 7 to the 3/2 minus what happens when I plug a 1 in here. 1 to the third is 1, 1 minus 1 is 0, 0 to this power is 0, 0 times this is 0, and oh look, we get the same answer. Okay? I don't really care if you evaluate with u-bounds. If you find u-bounds confusing, don't put any boundaries and just find the antiderivative. The antiderivative of u to the 1/2 is 2u to the minus 1/2. And then do that replacement. So 2 over square root of x to the third minus 1, because this was negative, so it goes on the bottom, 1/2 square root, from 1 to 2. Right? So no bounds or u bounds. If you put x bounds here, you lose points. So don't put x bounds on your u integral. Put u bounds in. To find the u bounds, you take these x values and plug them in here for x to find out what u is equal to. Alrighty. So here, just a little thoughtful for you. I have here a note that it would be nifty to do a little quiz here, kind of an exit ticket thing. And I'm not going to do them. I'm going to show you what I think would be an appropriate quiz. There's the first question. There's the second question. And there's the third question. Okay. Inverse tangent. U sub, where are you, is ln of t. How come? Well, what's the derivative of ln of t? 1 over t dt. So that's a u sub with that inside function. This is inside the sign. Now, what about this? Do we recognize that as someone's derivative? Nope. But we should recognize it as one of our Pythagorean identities, rewritten. So this is going to be cosecant squared x minus 1 dx. And this is negative cotangent minus x plus c. There's a lot of stuff to know. There's a lot of stuff to know. And you need to know it. All right. Have a wonderful day, everyone. I look forward to hopefully you show up for the next video.